Swayam Prabha. Digital India. Educated India.
Good afternoon and welcome to the NPTEL online certification courses. This particular course is dedicated to the subject domain of environmental degradation of materials and surface engineering. We are already into the module 7, and until module 6 you would have listened to the various aspects of surface dependent properties, their origin, their classification, their various utilities and importance, and also how they are evaluated, tasted, and so on. Now, we basically are going to talk about, in today's lecture, we are going to dedicate the entire time in understanding the nuances of surfaces and interfaces. So, what is it and why do we have to pay more attention when we talk of surface-dependent properties? Why do we talk about it? The first question obviously arises that why should surfaces arise at all? Why do we have to worry about surfaces? Now, whenever we talk about a finite size of an object, the very definition of finite means that the particular object has a specific dimension and it ends somewhere. And where it ends, the continuity breaks. So surfaces or interfaces, basically they form during various material processing techniques like liquid casting or coating or deposition or synthesis of various types of materials in small or large volume, deformation processes, consolidation of powders, and of course various thermomechanical treatments where you apply both thermal and mechanical activation. So as you see here in this view graph, they are randomly chosen techniques or processes. Like this is where you are pouring liquid hot metal at very high temperature and this is easily, if it's steel, you are talking easily about over 1100, 1200 degrees centigrade, and you are pouring into a mold so that a particular casting is formed of a near shape or near net shape configuration. So you can do continuous casting. Say for example, the same liquid metal may be poured into a turn dish, and from that you carry the hot metal through various rolls and various configurations of casting rolls. And instead of producing a semi-finished product, you might end up like an ingot or a starting material. Instead of an ingot, you actually can form thin sheets or wires or rods and coil them up, and actually by virtue of which it actually can be ready for shipping to the destination. So bead casting in conventional mode or continuous casting, then you can think of plasma-based synthesis, various forms of spraying operations for surface coatings. Think of electroplating, where you form thin films or thin coatings. Various high energy and direct energy beam synthesis techniques like electron beam synthesis, galvanizing, for example, on steel sheets. You can also make a complete three-dimensional product out of powders through a process called sintering, where you consolidate the individual powder particles into a bulk and a rigid structure. So when we do all these, we invariably end up creating surfaces and interfaces. In other words, if you're talking about a solid, it would definitely have either a continuity ending at some point of the bulk and interfacing with either a liquid or a gaseous state material. So it could be a solid vapor interface, it could be a solid liquid interface, and even within the solid, various forms of aggregates, we can also have solid-solid interaction or interfaces. So the boundary between two phases typically can be a surface or interface, and this boundary actually means a change of state of the matter, like liquid vapor, as I said, or atomic arrangements from crystalline to non-crystalline, or even crystalline to another form of crystalline structure. And certainly it can also invoke the change in composition. Say, for example, you may have a solid dipped in a liquid water or acid or some other forms of liquid. The thickness of the so-called interface is something which we often wonder as to how thick, or is it truly a monoatomic layer, or could it be more than a few atomic layers? So typically in real materials, this is rarely a single atomic plane, because then it becomes too difficult to distinguish. But in very special, particularly high-end semiconducting devices, you might require an interface which actually is monoatomic or just a few atomic layer thick. But we'll have some more discussion on this as to how thick the interface could be. But typically one assumes that it is only a few atomic layer thick, and but in certain applications where you actually want certain epitaxial growth or protection of the surface, then the interface could be thicker. It also can be very sharp, in the sense the orientation change could be very sharp, or it could be diffused, where you have change in both composition as well as orientation over a certain thickness dimension. Now, surface and interfaces are basically used conveying nearly the same connotation, but it's not 100% the one and the same. So typically the interface is more used when you are talking about boundary between two condensed phases, whereas when you talk of solid vapor or solid liquid interfaces, then you say surfaces. We also have to realize that the surface that we are talking about essentially is a two-dimensional entity. It is going by the hierarchy. You certainly will have x and y dimension, but not thickness dimension. Though I immediately talked about thickness dimension, but that's very small. That's exactly a very thin region. Now, when you talk of the manifestation of surfaces, the first thing that we have to understand or keep in mind is that no matter how big or small, think of a solid, and that solid is made up of, let's say, it can be in principle be made up of atoms or ions or molecules or radicals, or even in the limit it could be a few atoms put together in the form of a monomer and so on. But whatever is the species, which is basically the building block which is repeated in 3 dimension to make the solid, that particular species inside, somewhere inside the bulk, will have pulls and pushes from all over, from the entire 360-degree dimension. In other words, if you think of an atom which is truly at the center, this atom is going to be facing forces of attraction and repulsion from all sides, from entire 360-degree. But on the other hand, if you compare the plight of an atom which is right on the surface, and when it is right on the surface, as you can see here, this blue atom, when it's in the middle, it is having identical surroundings all over, or at least push and pull from all over. But at the surface, the same atom now is likely to enjoy at least 1 degree of freedom, which is the missing plane either on the top or on the bottom or side and so on. So as a result, there will be evolution of unbalanced or unsaturated forces or energy vectors, energy lines somewhere on the surface. The cumulative effect of that put together is what is known as surface energy or surface tension. So it can be expressed in terms of linear forces or planar forces. So as I said, we could have solid liquid, solid gaseous, solid vapor, in other words, or solid vacuum, and various kinds of interfaces. And the key to the origin of the surface energy are these unbounded atoms. And it is because of this reason the surface atoms are more reactive, more prone to take part in reaction, and that's why they are believed to be in high energy state. And this high surface energy that we are talking about, essentially, as I said, is a cumulative effect per unit length or per unit area. And this is very conventionally and very universally explained in terms of the Young's equation, wherein you see that if you have a droplet of a liquid on a solid surface, then you have all the three phases, they are kind of next to each other. Here is a solid substrate on which the liquid droplet is located, and on top of the liquid droplet you have the vapor, the gaseous state. And as a result, one can define three kinds of forces between the solid and the liquid, between the solid and the vapor, solid substrate and the vapor, and the liquid and the vapor. And each one of them will have a tensor, and at this particular triple point junction, you can easily see that these three forces are balancing each other such a way that this droplet takes a particular shape. And this shape can be easily defined in terms of the angle subtended between the force vector here, which is between the solid and the liquid, and the one between the liquid and the vapor. And this angle defines whether this liquid is going to spread very easily or it is going to ball up in the form of a near sphere. So we also have to understand that the liquid droplet here is different than the solid that we are talking about. And for example, if this is a crystalline solid, then the substrate will have atoms or molecules or ions repeated in 3 dimensions in a particular geometry, and that's how we make up the crystalline structure. Whereas this liquid droplet on top, in all likelihood, and I mean that's for sure, will not have the same 3-dimensional periodicity, but it certainly is composed of molecules or some species, and their arrangement and their interatomic forces and their configuration or the angle subtended, they are going to be very different than the solid that we are talking about. So as a result, obviously these two, just because of the difference in chemistry, composition and the bonding forces, are not going to assume the same shape even at the same temperature and pressure, and hence arises the need to define the surface energy. And again, the same thing that we were discussing a minute before, the Young's equation. So that allows us to essentially determine the geometrical factor theta, which is the angle subtended between the forces as can be seen here. And we can easily make out that depending on the chemical nature of the droplet and the solid and their interaction at the interface, the angle that is subtended varies. And hence this angle, so-called the wetting angle, is a very important and convenient parameter to describe the level of interaction and the kind of interaction between the particular solid and liquid which are in discussion now. So the next part is why do this, or what is a measure, what is a variation of these surface energies that we are talking about. We are all aware that crystalline solids, all crystalline solids randomly chosen, will invariably belong to one of the 14 Bravais lattices. We are not discussing those crystal structure or structure of solids in this lecture, but I'm sure all of you can easily relate to the crystallinity or crystalline description of solids, and you would definitely be able to recall that in the let's take up one of the most simpler situation of cubic, and in fact if we go slightly deeper, not simple cubic but either face centered or body centered cubic arrangements, then what we realize is that the crystal, depending on the section we have chosen or the crystallographic plane of reference we are discussing, will have different types of geometry or configuration of atoms, the way they pack themselves. For example, here we can easily see that 111 is the crystallographic plane. Assuming this is an FCC crystal, will have the largest packing, and as a result we see any atom which has identical surrounding is actually surrounded, one is surrounded by 6, so it actually enjoys the one in the center enjoys 6 bonds with the 6 neighbors. So the contribution per atom is going to be half of that, which is 3 per atom. And if we assume that the bond energy or the bonding energy or the bond strength is epsilon, then typically the internal energy per bond will be 3 epsilon over 2. Now this configuration is, or this description is true for 111 crystallographic plane in an FCC Bravais lattice. In the same Bravais lattice, if we move to another plane, that means I have taken a section which is geometrically different and subtending a different angle. And there we'll see that typically it will show a very different configuration. I mean, this is not necessary that it has to be an FCC. Even in a BCC configuration, one can easily show that, I mean, similar situation may exist. But depending on, I mean, if it's cubic, then we know that as we move from 1 HKL to H1K1L1 or H2K2L2 crystallographic planes, then the atomic density per unit area and even atomic density along a particular line or linear density of atoms, they may vary, and they do vary. So as a result, the final surface, which is manifesting on the top as the free surface, if it is 111 or 200 or 220, then we can easily make out that the unsaturated bond or the accumulation of the unsaturated bonds at the surface is going to be different. And if it is different, then obviously the surface energy, which is either a cumulative effect along a line or over the surface area, is going to be different. So the overall bulk of the crystal or the bulk of the solid will have two components now in terms of the Gibbs energy, which we assume as the index of stability of the solid. So if we say that Gibbs energy basically is a concept which signifies the relative stability of a solid or any entity, be it a phase or a bulk solid, then it will invariably have at least two specific components. One is related to the bulk and another to the surface. And the surface Gibbs energy for the surface will be connected with the interfacial energy, which we know can be easily derived and can be shown that in liquid we see isotropy and near isotropy or almost isotropic situation, where in solid this will never be 100% isotropic. For the simple reason the atomic packing density varies from one crystallographic plane to another. So in a nutshell, what we have to understand is that if the bond energy is very high, then obviously we understand or we assume or we do experience that that particular crystal will have a very large melting temperature. And if it has a large melting temperature, then automatically what follows is the heat of sublimation is fairly high, and hence the accumulation of unsaturated bond energy on the surface also will be high. So typically for solids which have higher melting point or higher heat of sublimation will definitely have higher surface energy. Now, so I was referring to the manifestation of the solid liquid interface in two forms or two or multiple forms, but here are the two extremes. One is the so-called water or liquid loving interface, the other one is liquid repelling or hating interface. So when it is loving, that it simply means that you just drop a particular liquid drop on top of a surface and it immediately spreads. Typically the experience that we see when we actually allow an ink drop to be spread over a blotting paper. So if I have a surface which is very hungry for liquid, immediately if you put a droplet, and that droplet will spread, and that's exactly why the blotting paper was invented. So the pores actually are very much ready and willing to absorb the liquid on the surface. But on the other hand, so this is one extreme, and in the limit actually the angle, the so-called wetting angle that is subtended, or the theta that we were talking about, could be as small as just a few degrees, even less than 10 degrees. And if it is truly super wetting or super wicking type, which means it will have zero wetting angle, you won't see a hillock forming at all, and hence the wetting angle will be close to zero. The other extreme could be hydrophobic, when as if the surface fears water or hates water or repels water. The typical example is the water droplet on say lotus leaf that we see floating on the lakes. So it can be a lotus leaf, it can be a rose petal. In all these cases, nature actually knows how to protect its own precious resources. So the water leaf has to receive sunshine, has to also collect carbon dioxide for photosynthesis, and on the lake, if it gets covered with water or ice flakes, then the process of photosynthesis is affected, which nature certainly doesn't want. So in order to prevent any such unwarranted situation, nature creates a very fine surface texture and surface structure so that the water droplets cannot spread, leave alone spreading, cannot even rest very in a stable configuration. So the droplet eventually, with slight perturbation, will move away from the surface, and the lotus leaf is exposed to sunlight and to receive sunlight and also absorb carbon dioxide from the atmosphere. So in order to actually ensure this, and borrowing from nature, one can also synthetically create hydrophobic surfaces, and these hydrophobic surfaces can be tailored such a way that the wetting angle can be not only high and higher than 90 degree, it can be close to even 150 or even higher than 150 degree. So in the limit, you can create a super hydrophobic surface like what we see on rose petals. In fact, more than I would say lotus leaf, the rose petals will never allow any moisture to condense. Even if it condenses, it will trickle down. It will never cover the petal. So there the wetting angle is 150 degree. But what we have to be careful about is to understand how do we measure the angle. So, and that's where we cannot afford to make a mistake. So in a situation like this, we are showing certain thickness here, but actually imagine this thickness is negligent. So you can't define where is your tangent. So the tangent actually will be in that case parallel to the solid substrate, and hence the angle subtended will be near to zero. So that's complete wetting, the extreme, super hydrophilic. On the other hand, if we take any real liquid droplet and spread it over the surface, so it will subtend varying degree of angles, and in the limit it actually can, and as it changes from super hydrophilicity to hydrophobicity, the angle increases, and this is how we measure the angle subtended. So in other words, we have to ensure that the angle actually is part of the liquid for which we are trying to measure the angle. So if you take the conjugate angle, then you are making a mistake. Okay, I also would like to draw your attention to another important set of these tables. Actually throw some numbers, and you will be easily be able to understand as to how do surface energies vary. So remember that the energy is expressed in SI units or MKS units in millijoules per meter square. So the measure is based on certain testing routine, but these are the numbers which are the magnitude of the surface forces that we are talking about, surface energy we are talking about. So they are basically, as you see, copper, aluminum, zinc, tin, lead. So which way are they changing? They are changing in terms of their melting temperatures. So 1080 degrees, 662 or 427 and 232 and so on and so forth. So likewise, the corresponding surface energy values also decrease as the melting temperature decreases. And you see for stainless steel or various other very important solids, I mean, we have been only giving reference to steel or metals, but that's not fair, because as an engineer, we deal with all kinds of engineering materials, and we know very well that in simple terms, all possible solids which have engineering utility in their pure form can be divided into three major baskets: the metals, the ceramics, and the polymers, depending on the nature of bonding or the kind of bonding characteristics. So in case of metal, we have a free electron cloud. In case of polymers, we allow the neighbors to share the electrons between the nearest neighbors. So that's covalent bonding. And in case of ceramics, we see a predominant nature of electrons getting transferred from the cation to anion, and that's how they form a non-directional bonding of very high value. So when you talk of porcelain, typically the material which is used for for various storing various liquids, chemicals, and so on. The most important property is that non-wetability. So you would not allow anything to wet the porcelain surface. For example, we also see those porcelain caps or relay structures which are used for high tension lines, which are used to tie the high tension lines on the poles on the large towers through which we actually allow the conducting wires to go along the countrysides by kilometers and hundreds of kilometers and so on. So there the structure, the pole has to be of metal because you require certain engineering properties like strength and toughness and durability and so on, and also ease of fabricability. So you cannot create a complete tower out of porcelain. So you create a tower out of metal, but you can't afford to allow the conducting wire to come directly in contact with the tower, which is of metal, because then people touching it will get electrocuted. So you have to have an insulation, and that insulator is the porcelain caps. So here the property that is of biggest interest is not just the hydrophobicity, but also insulation property. So such kind of polymers, white wares give you very high insulation property or insulation energy or insulating energy. But the point that I'm trying to make here is that the porcelain also is used for all sanitary wares and all other in the toilets or in various other utilities, primarily because of hydrophobicity. Is because they don't wet. Even if you take very aggressive liquids containing some halides or sort of diluted acid solutions and so on, they are safe. So this is how the properties of the solids vary, and it's entirely because of the changes of the variation of the surface energy and hence a contact angle, which in turn arise because of the saturated bond or unsaturated bond cumulative effect of that. Now, how do the surfaces arise? I mean, if we are talking about a crystal for a while, let's pay our attention to the crystal growth mechanism. So imagine just like the roof of your house, so you can have terraces. So these terraces are made up of crystal blocks, and for our convenience, we assume that this block is actually these are atoms are manifested in the form of Lego blocks, basically parallelepiped blocks. So they can fit in to various grooves and surfaces or edges available. Now, in general, it is known that if you want to create, if you want to place a single block on top of an available flat surface, this is the most unstable configuration, because for every such block, you are creating 5 new surfaces, which is a very difficult proposition, because then nature has to allow creation of new surfaces. And always remember, creation of a new surface is against nature's natural tendency, because you have to spend energy from whatever little you have saved for creation of material or synthesis of material. Instead, if you put this block into this groove here, or this ledge here, or this particular kink here, or in these ledges here, then they are more stable. So in such situation, basically the surface energy or the surface tension, the linear form of a planar solid surface will choose the way to grow depending on the crystallographic orientation of the surface. And we also have to remember that energy wise, the bulk energy of course is the least, surface energy is higher, the step energy as we are seeing here is still higher than surface energy, normal surface energy, the overall surface energy, and the kinks or atom energy is the highest one. So this is least stable, the adatoms or the individual atoms on the surface least stable, and of course this is the most stable configuration. And surface energy actually is contributed because of the effect of opening up unsaturated bonds and lack of continuity at the surface. So if you take a cross section, then you see an interesting feature. Even if the bulk is crystalline, there's every likelihood the top surface, which either could be smeared because of mechanical deformation or accumulation of impurities from the atmosphere, actually could be a layer which lacks in three-dimensional periodicity. So usually when you are dealing with a material which has been freshly worked, the bulk, the interior may be fully crystalline. The surface deformed layer, which probably is either due to machining or rolling or forging or whatever, has a fairly deformed layer, crystalline though, but with a lot of crystalline defects. And then you can have a so-called Bilby's layer, which essentially is a smeared layer. Then a thin layer of oxide or sulfide or some such compound layer formed due to interaction with the atmosphere is quite possible. And then you may also have certain amount of adsorbed gases and water vapor on the top. So now look at the numbers. So for the first layer, we are talking about only about a nanometer, 10 raised to minus 9 of a meter. So just you're talking about 1 or 2 layers, that's all. Then you may have about 10 or maybe few tens of nanometers. And this is where you can have a very highly deformed and smeared layer. And also the top may be decorated with a oxide or hydroxide or sulfide or such a layer formed due to interaction with the atmosphere. The worked layer, if it's freshly machined or deformed, may be bigger, and as you can see, it's bigger by orders of magnitude. We are now talking about a few micrometers to almost 100 micrometer compared to the few to 100 nanometers. But then below that is a bulk surface, the bulk material. So this is very important for us to know that all the surface related phenomena, call it degradation or reaction or reactivity, all of these primarily is related to this surface characteristics. Now, I'm not going to discuss surface dependent properties because I'm sure Professor Datta Majumdar would have already covered those areas, but it's important for us to classify very broadly all surface dependent properties, at least in these special groups. One can also come up with some other classification model, but I would take the liberty of saying that as far as surface properties are concerned, we are concerned with the various physical properties like roughness and color, adhesion and so on. On the other hand, we can have a large number of properties which are related to mechanical interaction, the hardness, micro hardness or small scale hardness. Rupture basically depends upon the state of surface, and mostly for brittle materials this is important, which initiates at the surface. Wear or abrasion is a very important surface dependent properties, and so is fatigue, but fatigue as such continues until the bulk but initiates primarily at the surface because of the surface stress condition and interaction with the applied stresses. And then for chemical, we can think of corrosion, chemical reactivity, high temperature oxidation, tribocorrosion, and so on and so forth. The one very important part that I would like to convey here is that I told you that surface energy or reactivity arises because of the difference in structure and atomic bonding situation at the surface compared to the core or the bulk. And surface engineering or the surface related properties arise primarily because the surface has usually the highest concentration of stresses, and also compositionally and structurally they are different than the bulk. So if we want to improve upon surface dependent properties, and these are the various randomly chosen surface properties which are of interest to us for various engineering applications. But if you want to improve upon them or tailor them, then what we do basically is to change either the microstructure or structure or constitution or the composition of the near surface region. And the near surface region is sort of a tricky concept because depending on materials, in the limit it could be as thin as a few nanometers and a few atomic layers only, and on the other extreme it can be even a millimeter. So we are talking about 6 orders of magnitude differences to be able to describe truly the characteristics of surface and surface engineering. So I think with that we'll end saying that these are the questions for you to ponder over. What do you mean by surface and interface? We should be very clear. How does surface arise or form? I'm sorry, there's a mistake. Arise or form. Then what is the surface? What is surface energy? What is its origin? why do metals have more surface energy than polymers? What does the bonding characteristics, strength or melting temperatures, what do they have to do with surface energy? Why do liquids, for example, always have lower surface energy than the corresponding bulk solid? Why is it so? And how does surface energy influence various physical and chemical properties of metals or solids in particular? And how do the differences between hydrophobicity and hydrophilicity arise? And what are the uses, engineering uses for them? Right. So these are the references, and thank you very much for your attention.